Something unusual has been happening inside the offices where America's earthquake and volcano monitoring actually gets done, and it isn't any single event making headlines. It's a shift in posture. Across multiple independent research groups, from seismology labs to volcano observatories to coastal geodesy teams, monitoring schedules that normally run on routine, predictable cycles have quietly been intensified up and down the West Coast at the same time. No single agency has declared an emergency. No evacuation orders have gone out. But when you talk to the researchers actually running these programs, a consistent theme keeps coming up. Several independent lines of monitoring data, unrelated to each other on the surface, have all shifted in the same direction within a short window, and scientists who spend their careers being cautious about coincidence are no longer entirely comfortable calling it one. To understand why this matters, you have to understand how West Coast monitoring normally works, because it's built around the assumption that different hazard systems, earthquakes, volcanoes, and slow tectonic creep operate largely independently of each other on any given week. Seismologists watch fault networks. Volcanologists watch magma chambers and gas emissions at specific peaks. Geodesists track how the ground itself is physically deforming using GPS networks anchored into bedrock. These are separate disciplines, staffed by separate teams, publishing in separate journals, and most of the time, their data simply doesn't move together, because the physical processes driving an earthquake hundreds of miles from a volcano rarely have anything to do with each other. That's what makes the current moment different. Over a compressed stretch of recent weeks, elevated signals have shown up simultaneously across several of these separate monitoring systems in different locations, using entirely different instruments, and the overlap in timing is what's caught researchers' attention more than any single reading on its own. Start with the seismic side. Fault networks along multiple segments of the West Coast, from Northern California up through the Pacific Northwest, have recorded clusters of small earthquake activity that, individually, wouldn't be remarkable. Minor swarms happen constantly along active fault systems and rarely mean anything on their own. What's drawn attention this time is the geographic spread, activity showing up across several historically distinct fault zones within roughly the same window, rather than confined to one system the way a typical localized swarm would be. Seismologists are careful to note that correlation across distance doesn't automatically imply a shared cause. Fault systems can and do behave independently even when their activity happens to overlap in time by chance. But the spread has been broad enough and coincided closely enough with changes in other monitoring systems that several research teams have decided it's worth treating as a pattern to actively track rather than dismissing as background noise. At the same time, volcano observatories watching some of the region's most closely monitored peaks have reported subtle but measurable changes in gas emissions and ground deformation, the two signals volcanologists rely on most heavily to gauge whether magma is moving closer to the surface. These changes, on their own, sit within a range observatories describe as elevated but not alarming, the kind of signal that gets logged, discussed internally, and watched more closely without triggering a public alert level change. What's unusual is that more than one monitored volcano along the West Coast has shown this kind of subtle uptick within the same general time frame, prompting internal comparisons between observatory teams that don't typically coordinate this closely unless something has specifically drawn their attention to doing so. Then there's the slower, quieter signal that doesn't make headlines the way an earthquake or a volcanic alert does, but that geodesists say may actually be the most significant piece of this puzzle. Subtle shifts in GPS-measured ground deformation along sections of the coast where scientists track the ongoing, gradual buildup of tectonic strain. Networks of GPS stations anchored into bedrock across the region continuously measure how the ground itself is moving, millimeter by millimeter, as tectonic plates grind against each other deep underground. Small deviations from the expected, steady pattern of that movement can indicate that stress is redistributing in ways that don't match standard models, and researchers monitoring several of these stations have flagged deviations worth a closer look, again, within the same general window as the seismic and volcanic signals. Individually, seismologists, volcanologists, and geodesists studying each of these signals separately have all reached a similar, carefully worded conclusion. Nothing here, on its own, represents an immediate threat or a confirmed precursor to a major event. That's an important distinction researchers keep repeating, because it's easy for a story about multiple monitoring systems lighting up at once to get flattened into something that sounds far more alarming than what's actually being described. What has genuinely changed is not the danger level, but the coordination level. Researchers who normally work in separate silos, checking their own instruments, publishing their own findings, are now actively comparing notes across disciplines, specifically because the overlap in timing across otherwise unrelated systems is unusual enough to warrant that kind of cross-checking. This is where the science gets genuinely interesting, because it touches on one of the more debated questions in Earth science: whether and how stress changes in one part of a tectonically active region can influence activity in a seemingly unrelated part of the same region. Researchers have documented cases elsewhere in the world where a significant earthquake on one fault measurably altered stress conditions on a completely separate, sometimes distant fault, occasionally triggering activity there with a time lag ranging from days to years. Similar stress transfer relationships have been proposed, though less conclusively demonstrated, between tectonic activity and volcanic systems, since both ultimately respond to the same underlying crustal stress field, even when the specific physical mechanisms driving an earthquake and a volcanic eruption are quite different. Whether something like that broader stress transfer relationship is playing out across the West Coast right now is exactly the open question driving the current cross-disciplinary comparison, and it's a question none of the individual research teams could meaningfully answer working in isolation. What makes this moment different from routine monitoring isn't the existence of any single anomaly, since fault swarms, volcanic gas fluctuations, and GPS deviations all happen regularly on their own without indicating anything unusual. It's the decision by multiple independent research groups to formally increase monitoring frequency and begin structured data sharing, specifically because the pattern across systems looked different enough from normal background variation to justify it. That's a meaningfully higher bar than any single team simply noticing something interesting in their own dataset, and it's part of why this development has moved from internal scientific discussion into public-facing monitoring updates. Emergency management agencies across the affected states have been briefed on the situation, and their public messaging has mirrored the scientific community's careful framing. This is a period of heightened monitoring, not a period of heightened alert level or public warning. Agencies emphasize that standard earthquake and volcano preparedness, the same guidance that applies at any time along an active tectonic region, remains the relevant guidance now. What's changed is the intensity of the underlying data collection effort, more frequent satellite passes, additional temporary seismic instrumentation deployed to fill gaps in permanent networks, and more frequent joint briefings between agencies that don't typically coordinate this closely. There's a technological dimension to why researchers are even able to notice this kind of cross-system pattern in the first place, and it's worth understanding because it reflects a broader shift happening across Earth science generally. A decade ago, the kind of rapid, cross-disciplinary data comparison currently underway would have been considerably harder to coordinate. Different agencies historically maintained separate data systems, different formats, different update frequencies, making it genuinely difficult to lay a seismic dataset, a volcanic gas emission record, and a GPS deformation curve side by side and look for overlapping, timing with any precision. Improvements in shared data infrastructure and more standardized reporting formats across agencies have made this kind of cross-referencing dramatically faster, which is part of why a pattern like this is being noticed and responded to now in a way that might have taken considerably longer to surface in the past or might have gone unnoticed entirely. Researchers are also careful to place this moment in historical context, because the West Coast has seen periods of elevated, multi-system monitoring activity before that ultimately resolved without any major event occurring. Fault swarms have flared up and quieted down without producing a significant earthquake. Volcanic unrest signals have elevated and then settled back to baseline without an eruption. That history is part of why scientists are resisting the urge to treat the current pattern as inherently more significant than those past episodes, even while acknowledging that the specific combination of simultaneous signals across 3 separate monitoring disciplines is not something they recall coordinating around quite this closely before. For the scientific teams involved, the coming weeks are less about predicting a specific outcome and more about determining whether this cross-system pattern strengthens, stabilizes, or fades, the same 3 possibilities that have played out in past periods of elevated activity along the coast. If the pattern fades, it will likely be filed away as an interesting case study in cross-disciplinary monitoring rather than a precursor to anything. If it strengthens or persists, it will shape how monitoring agencies think about coordinating across seismic, volcanic, and geodetic disciplines going forward, regardless of whether it ultimately connects to any specific hazardous event. Either way, researchers say the value of having watched this closely, together, across disciplines that don't usually compare notes this actively, is already changing how West Coast monitoring gets done. That shift toward closer, more integrated monitoring is likely to outlast this specific episode, according to several scientists involved in the current effort. Even if the elevated signals settle back to baseline in the coming weeks, the way past episodes often have, researchers say the infrastructure and working relationships built to compare data across disciplines this quickly won't simply be dismantled once the immediate pattern resolves. Several agencies have already discussed formalizing a standing cross-disciplinary review process, a recurring check-in where seismic, volcanic, and geodetic teams compare notes on a regular schedule rather than only during periods of unusual overlap, specifically so that future coincidences in timing, if they occur, get identified faster than this one did. There's also a public communication challenge researchers are navigating carefully throughout this episode, one that has as much to do with managing expectations as it does with managing risk. A story about scientists watching the West Coast more closely invites exactly the kind of speculation researchers are trying to head off, that heightened monitoring implies a hidden, unstated certainty about what's coming next. Agencies involved have been deliberate about publishing regular, plain language updates specifically to avoid a vacuum where public concern fills in gaps with worst-case assumptions the data doesn't actually support. That balance, being transparent that something genuinely unusual triggered this level of coordination, while being equally clear about what the data does and doesn't show, has become its own significant part of how this story has been handled from the agency side. For now, the instruments keep recording, the cross-agency comparisons continue on a rolling basis, and the researchers involved describe their current posture the same way emergency responders often describe the period before a storm's exact path becomes clear. Fully prepared, closely watching, and deliberately withholding judgment until the data itself, not speculation, tells them which way this is actually heading. It's worth noting how differently this kind of monitoring shift plays out compared to a generation ago, when the tools simply didn't exist to notice a pattern like this in anything close to real time. Older monitoring infrastructure along the West Coast was largely built discipline by discipline, seismic networks funded and expanded separately from volcano observatories, which were funded and expanded separately again from the GPS geodesy networks tracking long-term crustal deformation. Each system matured on its own timeline, optimized for its own specific hazard, and for decades that made sense, because the scientific questions each discipline was trying to answer were genuinely distinct. The trade-off, one researchers are only now fully reckoning with, is that a genuinely cross-disciplinary signal, something that only becomes visible when you look at all three data streams together, could have been sitting in historical records for years without anyone noticing, simply because no one was positioned to look across the boundaries between these systems the way current teams now are. That retrospective question, whether past instances of overlapping seismic, volcanic, and geodetic activity along the coast went unnoticed simply because nobody was comparing them side by side, has become its own quiet research thread running alongside the current monitoring effort. Several teams have begun the slower work of pulling historical datasets from all three disciplines covering the past few decades, specifically to check whether similar overlapping windows occurred in the past without triggering the kind of cross-agency attention this current episode has. If they find historical precedent for this kind of multi-system overlap resolving without incident, it will meaningfully shape how seriously the current pattern gets weighed. If they don't find clear historical precedent, that absence itself becomes a data point worth taking seriously. Public reaction to the increased monitoring has been mixed, according to officials fielding questions from residents across the affected states, ranging from residents who appreciate the transparency of agencies openly explaining why monitoring has intensified, to others who say the announcement itself, regardless of how carefully worded, has raised their personal anxiety level more than the underlying. Data seems to justify. Risk communication researchers who study exactly this kind of public response note that it's an almost unavoidable tension. Withholding information about unusual monitoring activity risks appearing evasive if something does eventually happen, while disclosing it transparently risks amplifying public concern beyond what the actual data supports. Agencies involved have generally chosen transparency, betting that clear, regularly updated, plain language communication does less harm over time than the alternative, even knowing it will generate exactly the kind of attention-grabbing headlines this story itself represents. Whatever the underlying signals ultimately turn out to mean, researchers say the structural change already underway, disciplines that historically worked in isolation now actively comparing data on a rolling basis, is likely to be the most durable outcome of this entire episode, regardless of how the current pattern resolves in the coming weeks.